All right, hello, welcome back. Today I want to talk to you about the repeated root scenario, right? What if we run this thing like we did a couple of times ago, and we find that we get the same root of our characteristic polynomial twice? Like, what are we supposed to do with that? Okay, last time I told you about the linear independence of solutions, right? If I was to, I think the one that I'm going to be eventually working with is y double prime minus 6y prime. Plus 9y equal to 0. What's going to happen if I go to my characteristic polynomial, factor, and get only one root that has multiplicity 2? Like, what am I supposed to do with this? Okay, what you're going to find is that if we have, you would think, using the technique we had done in the past, we'd say, well, y1 is equal to c1 e to the 3t, and y2 is equal to c2 e to the 3t. But these aren't linear independent, right? They're just going to be off by a factor of c1 divided by c2 or c2 divided by c1, whatever. One is a constant multiple of the other. They're not linear independent, and I need two linear independent solutions to get a general solution for one of these second order linear homogeneous differential equations with constant coefficients. Okay, so this is not going to work. I need to do a little something else. So what I'm going to ask you to consider is what's going to happen when I take the derivatives of something like t e to the t. Let's just consider y is t e to the t. We know how to take the derivative of this. It's not so bad. We're going to have to use the product rule, but it's definitely something we can do. Y prime is, well, I'll take the derivative of t and leave e to the t the same, and then I'm going to leave t the same and take the derivative of e to the t. Okay. And then y double prime is equal to, well, derivative of e to the t is e to the t, and I just took the derivative of that, so it's going to be plus e to the t plus t e to the t. And so you can see, if I had just the right coefficients on y double prime, y prime, and y, I could make this stuff cancel off, right? I've got t e to the t in each term, or in each of these derivatives. And I've got an e to the t, I've got e to the t's moving around, I've got y prime and y double prime. So this could be something that we could work with and get a solution. Okay? And that's pretty much what we're going to do. So if, I think that's not sufficient discussion on that. So the thought is if our characteristic polynomial comes back, the characteristic polynomial is something like r minus a squared equals 0. Okay? We'll have, like e to the at twice. That's what we would, c1 e to the at, c2 e to the at. So what I'm going to say is that we'll go down to here, and we'll say that y1 is going to be c1 e to the at, and y2 is c2 t e to the at. And that's how we're going to deal with this. And I'll show you over here, it works out quite nicely. Okay, so I go over here, I do all of this algebra, and I find that my characteristic polynomial has a repeated root r equals 3. So what I'm going to do, I'm going to switch color for a second. I'm going to say, well, I know, just because, maybe I've read farther in the book than you, or I've done this before in the past, and you not, but I know that this is going to be what the solution is. And so, like a lot of things in this course, I'm going to just kind of go through and reconvince myself and hopefully convince you that this is an effective technique, right? So, what am I thinking here? Oh, yeah. So I'm going to say that y1 is c1 e to the 3t. And then y2 is going to be c2t e to the 3t. Now, if this works, this will be nice because these are linear independent, right? You can't get t e to the 3t just by taking e to the 3t and multiplying it by a number. Not going to work, right? You'd have to multiply by a t. So they are linear independent. So if I can show that this is a solution to that differential equation, then I've got two linear independent solutions. I'll have a general solution. So what I'm going to say is that, well, I don't think that I need to convince you of the fact that y1 satisfies that differential equation. That's pretty much what we went through the whole last, the last time we were actually solving a differential equation. I believe that was 2 videos ago now. That was really what we were doing that whole time. So I'm going to just focus on y2. So y2 prime is going to be, well, I already did it, but of course I erased it. So how about c2 e to the 3t plus, all right, when I take the derivative of e to the 3t, that will induce another 3. So it'll be 3c2t e to the 3t. Okay. And then y2 double prime is going to be, all right, 3c2 e to the 3t. That's interesting. Plus another 3c2. When I take the derivative of this with respect to t, it'll just be 1. So 3c2 e to the 3t. And then that'll be 9. When I take the derivative of e to the 3t, that'll bring out another 3. And I'll have 9c2t e to the 3t. And then I'm going to figure out, well, what is y2 double prime minus 6 y2 primes plus 9y's. What does that equal? Okay, well, y2 double prime is 3c2 and 3c2 is 6c2 e to the 3t plus 9c2t. 3t. All right, that's my y2 double prime. 6y2 primes is going to be, I'm going to subtract 6 of these. So minus 6 c2e to the 3t. And then, well, yeah, when I multiply this by 6, I'll have 18 t e to the 3t. And then I'm going to add in 9y, so I'm going to be adding in 9. Okay, so there's no regular e to the 3t's, okay? But there will be 9 c2t's. Not sure if I've gone off of the shot. Yeah, okay, just slide down there a little bit. And notice, okay, 6 minus 6 on this level is 0, and then 9 minus 18 would be negative 9. You add back the 9, and that it does work out to be 0, like I'd hoped, right? And, well, this is pretty much what you do in the repeated root scenario. I think in the next video, I will tell you about what to do when your characteristic polynomial brings you back complex roots, and that's a little more interesting. So, if you're interested in that, just stay tuned for the next video.